Behind every app you use, there's a set of architectural ideas quietly doing the work. Microservices, caching, sharding, the CAP theorem. They sound like jargon, but each one is just a named answer to a real problem. How do we keep this fast, available, and correct as it grows? Today, 15 of them, one per slide. 15 building blocks behind every scalable system. We'll define each in one line, draw it, and give you the one rule to remember. Let's go. Microservices means splitting one application into several small services. In this example, orders, users, and billing. Each service runs on its own and, crucially, owns its own database. Because every service is independent, you can deploy and scale just the one that needs it. Here, users duplicates to 2 instances without redeploying the whole system. Services never share a database. Instead, they talk to each other over thin API links. The rule to remember: own your data, ship alone. A modular monolith is a single deployable application, but inside, it is split into well-bounded modules. Orders, users, and billing each own their own logic, yet they all ship together as one unit and share one database. Look closer and the boundaries are still sharp. Orders, users, and billing each keep a clear edge inside that one deploy. But unlike microservices, there are no separate boxes, no separate deploys, and no separate databases. One deploy, one shared database, and far simpler operations. In event-driven architecture, services do not call each other directly. Instead, a producer emits an event, something like order created, and publishes it to a central event bus or broker. The bus acts as a hub and fans that single event out to every interested consumer. An email service, analytics, and audit log. Crucially, the producer has no idea who is listening. It just fires and forgets. That is loose coupling, and because everything flows through the bus asynchronously. The whole system is a sync by nature. The rule: talk in events, not calls. Caching keeps the data you reach for most often in a much faster layer. A small, quick store sits between the client and the database, and every request checks that fast layer first. If the record is already in the cache, that is a hit, and the answer comes back almost instantly. No database trip at all. When it is not there, that is a miss. So the request falls through to the database and pulls the real value from the source of truth. That value is then written back into the cache, so the next call becomes a hit. The payoff is twofold: far lower latency for the hot data and a lot less pressure on the database. Load balancing spreads incoming requests across multiple servers, so no single machine becomes a bottleneck. A client sends a request. It arrives at the load balancer, which decides which of the 3 servers should handle it. Watch the first request. The load balancer picks server 1 and routes it there, keeping the spread even so no single server is overwhelmed. Now requests fan out to server 2 and server 3 as well. The traffic spreads across all 3, giving higher availability and the freedom to choose among many strategies. There is a dedicated deck on load balancing algorithms linked here for the full deep dive. Database sharding splits one large dataset horizontally across multiple databases, so no single machine holds every row. A shard router sits in front and uses a shard key, like a user ID or a customer number, to decide which shard owns each row. Here the router fans out to 3 shards. Shard A holds IDs 1 to 1 million, Shard B holds 1 million to 2 million, and Shard C holds 2 million to 3 million. When a record arrives, the router reads its shard key and prepares to send it to exactly 1 shard. The router sends the row to Shard B, while shards A and C stay quiet, because each shard stores only a subset. Writes and storage scale out across machines instead of overwhelming one database. Database replication copies data from a primary database to 1 or more replicas. Here, 1 primary on the left and 2 replicas on the right, joined by replication channels that keep the copies in sync. Every write lands on the primary first. It is the one place in the system where data is allowed to change. From the primary, each change propagates over the replication channels to replica 1 and replica 2. So every copy converges on the same data. Reads, meanwhile, can be served from any replica, which lets read traffic scale out across nodes. And if the primary ever fails, a replica is promoted to take its place. Redundancy and failover built in. The rule is simple. One writer, many readers. An API gateway is a single front door for every request coming into your system. Instead of clients talking to dozens of backend services directly, everything goes through this one gateway. Every request from every client hits the gateway first. One front door, no matter how many backends live behind it. On the way in, the gateway stamps each request with authentication, applies rate limiting so no single client can flood you, and hides your internal topology from the outside world. Then it routes the request to the right backend service. Here, service 2, one door, many backends. Command query responsibility segregation splits your data model into two independent sides. The top lane handles commands, writes that change state. The bottom lane handles queries, reads served from their own optimized views, two models, two databases, one system. A command arrives on the right side. It carries write intent into the right model, which validates and applies it to the right database, your single source of truth. On the read side, a query flows into the read model, which serves pre-built, optimized views straight from the read database, never touching the write path. Between the two, a projection watches the write database and asynchronously replays every change down into the read side. So the read database is eventually consistent, introducing a tiny delay in exchange for scaling reads and writes independently. The guiding rule: the read shape does not equal the write shape. Event sourcing flips the usual model on its head. Instead of storing just the latest value, you store every change as an append-only log of events. That log is the truth. Event 1, Event 2, Event 3, Event 4, Event 5. Each one written in sequence, never edited, never deleted. New facts only ever land on the end of the log. To get the current state, you replay the events from the beginning, applying each one in order, and the state rebuilds itself. Because nothing is ever overwritten, you keep the full history for audit. And you can time travel to any moment by replaying the log up to that point. This is the CAP Theorem, the foundational rule for distributed systems. It says a distributed system can guarantee only two of three properties at once: consistency, availability, and partition tolerance. Picture a triangle with C, A, and P at its corners. You pick any two of the three. C, A, or PA token circulates the whole triangle, reminding you the three properties are linked. But the catch is that network partitions are inevitable in the real world, so P is not really optional. When the network splits, the bottom edge breaks, and the system is forced to choose. You can keep consistency by refusing stale reads, or keep availability by answering every request with outdated data. You cannot have both during a partition. That is the rule. In a partition, pick C or A. Observability means understanding a system's internals from its outputs. A request flows through the service, and as it runs, three signals stream out to three separate pillars. Logs tell you what happened, a discrete, time-stamped record of events. Metrics tell you how much and how fast, counters and gauges aggregated over time, and traces show the request path end to end, the journey of one request across every service it touched. The rule: see inside from the outside. A request flows through the service, and as it runs, three signals stream out to three separate pillars. Logs tell you what happened, a discrete, time-stamped record of events. Metrics tell you how much and how fast, counters and gauges aggregated over time, and traces show the request path end to end, the journey of one request across every service it touched. The rule: see inside from the outside. When a single business operation spans several services, each with its own database, you need a distributed transaction. Two-phase commit locks every participant through a prepare phase, then issues a global commit. But it holds locks and blocks when a node fails. A Saga takes a different path. It breaks the work into a chain of local transactions. Server 1 commits its database change, then Server 2, then Server 3. Each step publishes an event that triggers the next. If every step succeeds, the Saga is done. But if Server 3 fails midway, the earlier services have already committed, so the system is left in a partial state. The orchestrator then runs compensating actions in reverse, undoing Server 2, then undoing Server 1, rolling the whole operation back. Locally, the rule is simple: all or nothing, but always with a way back. Resilience engineering is about designing systems that keep working when pieces fail. A circuit breaker sits between a caller and a downstream service. Right now it is closed, and calls flow straight through. When the downstream service starts failing, the breaker trips open, so calls stop hammering a dying dependency, and the failure cannot cascade into a full outage. Instead, traffic reroutes to a healthy sibling service or degrades gracefully. The rest of the system keeps answering. Retries and timeouts put a hard bound on every attempt, and bulkheads isolate services so one failure cannot swamp the rest. The rule: fail isolated, stay up. Clean architecture organizes your code into concentric layers. At the very center sit the entities, your fundamental business rules. Around them come the use cases, then the interface adapters, and finally the outermost ring: frameworks and drivers, your user interface, databases, and external tools. Each ring only ever knows about the ring inside it. The further out you go, the more replaceable the code becomes, and the core stays pure. The dependency rule is the heart of it. Arrows always point inward. The core knows nothing of the outside. That shields your business logic from changes in frameworks, databases, or delivery mechanisms. So the center of your system stays stable, portable, and testable. So there are your 15. Microservices and the modular monolith are two ways to cut a system up. Event-driven, caching, load balancing, sharding, and replication keep it fast and spread out. The API gateway, CQRS, and event sourcing reshape how requests and state flow. CAP, observability, and distributed transactions are about staying correct when things go wrong. And resilience and clean architecture are how you stay standing and keep the code sane. Here's the one idea to keep. Every one of these is just a named answer to a real question. How do we keep this fast, available, and correct as it grows? Learn the names, and you can reason about any system. So before you go, one question, and I genuinely want your answer. Imagine you're building a growing e-commerce backend. Traffic spikes hard on sale days, the database is sweating, and the payment service occasionally times out. Out of the 15 we covered, which 3 do you reach for first and why? Caching and replication? Circuit breakers? Sharding? There's a real case for a few of them, so make yours in the comments. And if this made the architecture finally click for you, do the one thing that really helps the channel. Drop a like, subscribe, and ring the bell so you catch the next deep dive. I'll see you there.